Assalamualaikum everyone. Okay, so this is the second part of the video. In the last part, we saw how we can implement a sliding mode control onto some system. The system was magnetic levitation system. In our previous example, if you haven't watched the previous video, you can go ahead and search for sliding mode control implementation on matlab-simulink. And we saw the results and we observed that the controller has some gains, some tuning parameters, right? So the different values of these gains will give you different results. Okay, so how do we know which values are best? Well, there are different methods. In this video we're going to go ahead and learn how to use optimization algorithms. Specifically, we'll be implementing genetic algorithm. There are a lot of different algorithms. For example, Aunt Clooney optimization, particles amount optimization, artificial bee Clooney, red fox, gray wolf, improved gray wolf, and a lot more. So you can use any of the optimization algorithms, and the method is similar. So let's get into it and see how we would be implementing this genetic algorithm to optimize these gains. Okay, so the first thing we will do is define an error like we defined in the controller part as well. So I'll be using this sum block, and I will be, since our feedback in control engineering is negative, so well, it doesn't matter if you can just uh, flip the values as well here. So well, the difference between the actual state and the reference state, that's your error. Okay, so I will just use a goto block to define an error e1. E1 is good enough. Okay, so I'll just make it global just in case. Okay, so that's error one, but I would use an ABS, that is the modulus part as well, so the error is always positive, because well, it could have a different direction, but for the optimization algorithms, if it is has positive direction or negative direction, it has some magnitude, right? So negative will not indicate that the error is reducing, it is increasing in the opposite direction. So I'll be just taking this absolute part, so for the sake of optimization. Okay, so I'll do this similar thing to the rest of the states. Okay, so let's just go ahead, press the control button and drag these things here. Okay, so let's go ahead and do this. So this is the error for the second state, this is the error for the third state. Okay, so let's define it as error 2, let's define it as error 3, and okay, so we are now we have calculated overall the three errors. Now we will be using a from block, and I'll again be using a sum. Okay, so I'll add another sum here, a plus sign. Okay, so I'll be receiving the error 1, error 2, and error 3. So that's error 2 and that's error 3. So I'll add all these errors together to get the ultimate final error. Okay, so what I did is I evaluated the error of each state and just combined these here. Okay, so here is my final error, which I can observe using this scope. Okay, so there is my final error of overall all of the states. So what I will use is I will use a block of two workspace. Okay, so I will use the block of this two workspace. If you observe this, that you are using this block, but there's a dot here. So what you do is go to this modeling part, or just press Ctrl E, go to modeling setting. Just ensure two things, which I described in the previous video as well, that this part is unticked. Okay, and you are sending the format as arrays. Okay, so and the rest of the settings are fixed step size with 1e minus 5, discrete time, no continuous states, and that's it. Okay, so these are your settings. So we are using a block of two workspace because our algorithm is in MATLAB code, and we need to send the data from our Simulink model, this is our Simulink, to our MATLAB workspace. Okay, so to workspace will indicate that our data will be sent from this Simulink to this workspace. Okay, from where we will use this data to compute the code. Okay, so yeah, so there it is, our complete error. So we need to well define some of the settings. We'll be sending the 2D array. Okay, and the rest of the settings are good enough, the same. So we'll just rename it to ERR or double R. Okay, you can rename it to whatever you want. So I'll just rename it to error. Okay, so the next thing I need to do is just well make these values generic to some variable b, a1, a2, a3, a4. Okay, sorry, there is no a4, alpha. So I'll just put double a here because well it doesn't matter, you can put single a as well, it's up to you. Okay, I'm not using single a, maybe somewhere at the back end it was defined, so all of these are giving errors. Okay, so I'm using these variables and these variables need to get value from the workspace or somewhere, otherwise this simulation will not run. Okay, so that's it. I'll just control S and save this part. So we are done with this, and yeah, okay, now let's go to MATLAB and see what we have to do. So we have a cost function here, which is a simple cost function, but I've recently just designed this new much better cost function, so we'll be using that. Okay, so the thing we have to do is in the sequence that we defined it here, we will define the variables again in the same sequence in this cost function. So the first variable is beta, a1, a2, a3 and alpha. So the names should be exactly the same. Okay, so if it's capital it would be capital, if it's small it should be small, and so on. If there are double a here, you would define the double a same at this point as well. So a2, although well, okay, a3, and then we have this alpha with double a. Just remove the rest or add more if you have more. Okay, so well basically well this is just for the display purposes, you do the same for here. Okay, so well for the display purposes you can have different name, but here you must have the exact same name, a1, a2, a3, and then you have alpha with a double A. Okay, so just remove the next. Okay, and then what you do is well you saved your file. Okay, and you know the name that is in the top left corner, so you copy this exact name. Okay, so I click, single click, wait, and then another click. So I control C, I I'll select the file with the exact same name. You can remove the SLX part. So this is the simulation file name, and it should be in the same folder as this cost function file and this genetic algorithm file. Okay, so all simulation file, the cost function file, and the third part, all of these should be in the same folders. So you define the variables and you define the file name, and then we have this variable. Okay, ERR or double R. So this is the same as spelling as this to workspace variable, and the rest will remain the same. Okay, you can go ahead and well look into the detail of what each command is doing. So if you change the spellings of this variable, be sure to change it at this point as well, line number 48. Okay, so you can just maybe retype all of this, or I'll just share the link in the description for this code. So I'm just scrolling it so you can have pause the video and go ahead and write it. Okay, so in every optimization algorithm we have objective functions. Okay, so there are four objective functions written here. So you will be using one at a time, of course. So for now we are using integral absolute error. Okay, so this is the integral absolute error. You could use integral square error, integral time absolute error, mean square error, whatsoever. Okay, or something as well, because every optimization algorithm needs an objective function. Okay, so the way it works is that we are telling the algorithm to try different values and tell us which value is the best. How would it know which value is the best? Okay, the way it would know is that the values, the combination of values at which this error is minimum, that value is the best value. Okay, so the overall aim, the overall objective of this optimization algorithm is to reduce this error. Okay, so this is the objective function that we have defined here. So integral absolute error, every time the error is integrated, meaning it will keep on adding, and you have to, the code is in such a way that it will try to reduce this error. Okay, try those values. So we are done with this cost function file, and now we'll go ahead and see what we have to do with this genetic algorithm file. Okay, so we have to define lower bounds and upper bounds here, and a little more things. Okay, so we have how many tuning parameters? We have 5 tuning parameters. So we'll be using this number of variables are 5 that needs to be tuned, and we need to define 5 lower bounds: 1, 2, 3, 4, and 5, and of course 5 upper bounds. So you need to see, well, algorithm will be testing the different values of these constants, but you need to define the domain of this test. Okay, for example, if I just give the bound, lower bound of 0 and upper bound of 100, well, the algorithm will try millions of combinations between this 0 to 100. Okay, otherwise it could go from 0 to infinity. That's not, well, not logical, right? So we have to define a boundary of these gains that you can try from hit and trial in the initial state, or you can just look, have a more deeper look into the model of your plant and get an idea of what these bounds should be. There are some systematic ways as well, but for now let's go ahead and give 0 to 10, because we saw that giving, well, near less than 10 values were giving a good result. Okay, so let's go ahead and well, the first variable is for the first constant here, well, not the hair, but more accurately I would say that the first k1 is the hair, b, then a1, a2, a3, and alpha. So let's go ahead and define the lower bound for b is 0, the upper bound for b is 10, lower bound for a1 is 0, upper bound is 10 again, maybe lower bound for a2 is 0, upper bound can be 10, for a3 can be 10, and maybe for, well, the last part alpha could be 4, 3 is good enough maybe. Okay, so, and we will define the number of iterations. Well, that's a lot of iterations, we can maybe reduce it to 50. Okay, so that's it, and yeah, so we'll go to this editor part, and we'll just click this run button. Okay, and let's see what happens. So it says it is busy here. Okay, so we can open our Simulink file. It is running by default. Okay, as you can see, so it's running, and well, we can go to our command window, and here it is. So we can just double click this and see the final error. Okay, and I can just open the command window, maybe undock it, and move it to the left side and the scope to the right side. So what we see, observe here, is that for try number 3 or for try number 4, these are the values of the gains, and this is the corresponding error that resulted in. So the final error should be 0, right? Error should be 0. So the quicker it goes to 0, the better it is. Okay, so it will keep on trying all of these values every time. I don't have to do anything. I'll just keep running the simulation, and that's it. Okay, so I'll just stop this, and I'll make iterations equals to 2. You can increase, but for the sake of the video we'll just go ahead and see the final result. So it will just keep on running the videos, the iterations. Okay, so it did not stop. Let me try it again. Okay, so we're running with 2 iterations now. Okay, So there it is. Okay, so well, again it started from there, but so well, we will just wait and see. It is trying for different values of these gains, and every time it is saving the result, and ultimately in the end, the one that gave the minimum error, this will tell you these are the values, and you will use those values. So I'll just pause the video and wait for the final result. Okay, so we got the final results. Okay, so here's a graph as well that will give you the best value of this first variable, which was our b, and then we had a1, a2, a3, and then we had the alpha in the same sequence that we defined in our cost function. Okay, so our command window also says that there are our uh, best values. Okay, and then in the workspace we can also see here's the variable name with x. These are the best optimal values that will give you the best possible results in these many tries, 144 tries, to get even more better result. Maybe you can increase the number of iterations. For now we just decreased it to 2. So what we will do is this: we'll just copy these values and put them. These are the optimized values. Okay, so in the first value I will just copy paste this beta's value. Okay, then we have a1, a2, a3, and these are the values of a1, a2, a3, and then alpha. So we'll just copy each value, and well, up to this point, the work of the optimization algorithm is done. We don't need it anymore. We just need it for once to get the best optimal values. Once we have these best optimal values, well, we can just let go of the algorithm at this point. Okay, so well, okay, yeah, there it is. So from now on onwards, we don't need the optimization algorithm to run every time. It runs only once, and here we play it now. So let's see what kind of results we are getting. Okay, so the error is reduced. That's good. So let's see the individual states. Okay, so that's really nice. If we, well, in the last example, we saw that if we well make the value equal to 1 for all of these constants, 1, 1, 1, 1. So it takes about 7 to 8 seconds to reach to this final state. And well, we do have a steady state error, but that would be well resolved using integral sliding mode control. That's a different controller, but for using this same controller we got a better performance than before by using optimized gain values. Here you see also again we go to the final value at an earlier stage, here as well at an earlier stage. So just to confirm, I'll just go ahead and give different gain values, maybe one or whatsoever, to all of these gains, and you're using the same controller, same design, the results will change significantly. So we understand that the values of these gains play a crucial role. Here you see it takes a lot of time to reach the final value, and similarly for the second state it takes a lot of time, and for the third state as well. And if we see the overall error, well, there's a lot of error. Okay, so we understand that changing the values of these gains, well, it changes the result as well. So there are different algorithms. You can run another algorithm. Okay, you can run another algorithm other than this genetic algorithm and see what best values it gives you, and then maybe you can compare. For example, you can say that I run the genetic algorithm and I run the particle swarm optimization algorithm, and genetic algorithm gave these values, and using these values I got these results. Okay, and then you would say that particle swarm optimization gave me some different values. You put those values here and you see these results or this final error, and you do some of the analysis, and then you can compare which algorithm performed better with this sliding mode control. Okay, so you can apply multiple algorithms as well, and you can try different cost functions as well. Instead of this integral absolute error, maybe you can go ahead and see for this integral time absolute error as well, because if there is a steady state error at some stage, So it is always better to go ahead and use this integral time absolute error as well. So you can use different cost functions, and yeah. So once you have these results that you want, then you need to perform a graphical and tabular analysis. So that I will discuss in the next video of how you can do that. So for now, that's it. Allah Hafiz. Take care.